Welcome to this lecture. This lecture is given on this YouTube channel, electro_teach. This is a channel where we teach knowledge about electronics, computer, instrumentation, and mathematics. So today we are giving lecture on electronics, basics of electronics, and we are going to learn about energy bands in materials. We are going to talk about semiconductor materials. We're going to talk about conductor materials. We're going to talk about insulators. So we are talking about the characteristics of these materials and their properties as it affects electric current flow in them. We know the world of electronics. We have various materials used, but most importantly, semiconductors are the one that rules the world of electronics. And materials are classified based on their structure of atoms in the elements. So today we are looking at the effect of factors such as heat, electric field on this group of materials. Now, there are three main groups of materials that we are talking about. That is conductors, insulators, and semiconductors. And we are going to look at the valence, conduction, and forbidding energy bands in these materials. The electronic band structure of energy is a schema that is used to describe the conductivity of various materials, that is, conductors, insulators, and semiconductors. So the energy band structure, we have two important energy bands, that is the valence band and conduction band. And these are the bands that determine the behavior of the materials, whether a material will be conductor, semiconductor, or an insulator. So the energy band structure determines its behavior. There are, like I said, in solid materials, we have two energy band structures that are very important, the valence band and the conduction band. Now, these two bands, in between them, is what we know as the forbidding energy band that separates them, and especially in the semiconductor and insulators. Now, the valence band is the upper occupied band, and the valence electrons of an atom exist there. So the valence band may be either partially filled or completely filled with electrons. If it is partially filled, that means the material is able to move its electron from valence band to conduction band. If it is completely filled, it means there will not be such movement, and it's difficult for the atoms to interact with other atoms, and the material may likely be an insulator. All right. Now, above the valence band is the forbidding energy band in the crystal. And this is energy band. It is termed forbidding energy band because electrons are not allowed to exist there. Electrons don't exist there, but it's a gap of energy that separates the valence band and the forbidding energy, that separates the valence band and the conduction band. It is also called band gap. That is the gap of energy that the electrons from valence band we need to overcome to make a transition to the conduction band. So it's called the band gap. So for a material to conduct electricity, the electrons must make a transition from valence band to the conduction band before the material can begin to conduct electricity. So in the conduction band is the energy band immediately above the band gap, and electrons are allowed to exist there. And the electrons responsible for conductivity in a material are those present in the conduction band. So the band of energy possessed by the electrons in the conduction band forms the conduction band. Now, if you check the figure on the screen here, we could see a sketch, a graph of the band diagram for materials, generally speaking, for solid materials, generally speaking. We could see at the lower portion here, we have a band that is the lowest part. It is hatched. The hatching means that the presence of electrons in the band. And this band is the valence band, represented as E subscript V. The E here means energy and V represents valence. So valence energy band, that's what it means. Then we have a space after that, immediately after that, that is higher in energy. If you look at the vertical axis, it is energy. And you look at this space, which is termed EG, is a higher in energy level than the valence band. And EG means forbidden energy band or energy gap or band gap. So the energy gap here is a space, an amount of energy needed to be overcome by electrons from valence band and make a transition to conduction band before the material can conduct electricity. Now, above the energy gap is the conduction band. You can see that the conduction band is higher in energy than the energy gap also. So we can see it is also hatched. Hatching here means there is the presence of electrons. Now, the middle band here, the energy gap, is not hatched. That is to say, no electron is present there because electrons are not permitted to exist there. It's a forbidden gap. It's a forbidden gap. So electrons are not permitted to exist there. But electron can exist in the valence band and the conduction band. So the conduction band is the range of energy possessed by electrons that have made a transition from valence band to the conduction band. So that is the sketch that demonstrates this energy structure of solid materials, generally speaking. Now, we can classify solid materials as either conductors, insulators, or semiconductors. Now, for energy band diagram of conductors, we realize that there's going to be an overlapping of a valence band and the conduction band, because the electrons present in the valence band, they are already present in the conduction band. And that means the conductors or metallic elements, they are able to conduct at ordinary temperature because the valence band actually overlapped the conduction band. So there's no forbidden energy gap. That means electrons in valence band already made their way into conduction band at ordinary room temperature. The electrons are free, so they are able to navigate into the conduction band so they can conduct electricity easily without applying any external energy to the material. And this is a property of conductors or metals, generally speaking. And also the absence of a forbidden energy gap in the conductors makes it impossible to establish holes. There is no holes formation. If there is forbidden energy gap, that means electrons will have to leave valence band and navigate to the conduction band. As the electrons leave the valence band, they will leave behind holes in the structure or the atomic structure. But that is not happening here. So for that reason, it is difficult to manipulate metals, to manipulate their conductivities by application of external energy, such as increase in temperature or doping. It is not really easy to manipulate them because of the absence of holes in the structure. So that is a property of the metallic conductors. So we have the sketch here, the sketch illustrating the energy band diagram of conductors. We have the valence band, which is reaching up to this place, and then conduction band, which starts from also somewhere here up to here. So we can see there's an overlapping between the valence band and the conduction band. You can see the overlapping of the energy bands, meaning that this material ordinarily is a conductor. It can conduct at ordinary temperatures because the valence electrons have made a transition to conduction band naturally. Now let's look at the next energy structure, and that is the energy band diagram for semiconductors. For semiconductors, we see that there is a small energy gap between the valence band and the conduction band. So the small energy gap is of the order of 1 electron volt. 1 electron volt. That is quite small. So we have a narrow band gap between the valence band and the conduction band. And that means that electrons can easily make their way to overcome the small band gap and navigate to the conduction band, making them to conduct. That can happen at ordinary temperatures when external energy has been received by means of temperature. They have been received by the electrons as a form of temperature. Then they can break away from valence band and navigate to the conduction band. So external application of energy, such as heat, can easily help the material to conduct. And that is why these materials are termed semiconductors. So the valence band electrons can easily overcome the small energy gap and make their way to the conduction band, thereby conducting electricity. So with an increase in temperature, the forbidden energy band is decreased because electrons are liberated into the conduction band. At ordinary temperature at 0 degree Kelvin, the materials basically are insulators because no valence electron will navigate to the conduction band. But with the introduction of little external energy such as temperature, the electrons in the valence band will move to the conduction band. They become conducting electrons. And that is the structure of the semiconductors. Now, the last group of materials, they are the insulators. Now, before we speak about insulators, let's talk about what happens to semiconductor materials. When valence electrons navigate from valence band to conduction band, they leave behind holes. And as such, the materials can be easily manipulated by introduction of impurities into the crystal lattice to modify the electrical characteristics of the material. So this material can be easily doped by introducing either a trivalent impurity or a pentavalent impurity into the crystal lattice to make the material conduct better because of introduction of either electrons or holes into the system in the process called doping. And so that is why these materials are called semiconductors. They can easily become conductors by external application of energy or by doping. Now, energy band diagram for insulators. For insulators, we find out that electrons are tightly bound to their parent atoms. And in that condition, the electrons are not free to move or break away from the valence band. So they are tightly attracted to their nuclei. In other words, insulators have no free charge carriers. And free charge carriers we are talking about, they are nothing but the electrons. They don't have free electrons that can constitute electric current flow under normal conditions. So in terms of energy band, insulators have a completely filled valence band and have an empty conduction band. And they are characterized by a large energy gap of several electron volts. You remember in semiconductor materials, we have about 1 electron volts of energy band separating the valence electron band and conduction band. But in insulators, we have several electron volts in between. That is several energy gap, quantity is needed by the electrons in the valence band to make a transition to conduction band. They have to receive a large amount of energy before they can overcome the large forbidden energy gap that is present in the structure of the materials. So at ordinary temperatures, the insulators cannot conduct electricity. And that is because their valence electron is completely filled and their valence band is completely filled and the conduction band is completely empty. No electron is present there. So this is the structure of the energy band diagram. You can see a wide energy gap between the valence band and the conduction band. So the valence band have electrons present, while the conduction band doesn't have electron present. Of course, with application of external energy, a high amount of energy, the valence electrons in the valence band can actually make a transition to conduction band and constitute a current flow. But at ordinary room temperature, there's no presence of electrons in the conduction band. Now, the table here shows the comparison of the electrical properties of these three types of materials and their applications. We have the conductor, semiconductor, and insulators. Forbidden energy gap. The forbidden energy gap does not exist in conductor and is very small in semiconductor, about 1 electron volt. And in insulators, we have large forbidden energy gap, about greater than 5 electron volts. And conductivity. In terms of conductivity, conductors have high conductivity, 10 raised power minus 7 mole per meter. And for semiconductor, 10 raised power minus 7 to 10 raised power minus 13 mole per meter. For insulators, very low, 10 raised power minus 3, almost negligible. So that is the conductivity value. Resistivity for conductor is very low, for semiconductor is moderate, and for insulator is very, very high. Flow of current. Flow of current in a conductor is due to movement of free electrons. Also, in a semiconductor, we have free electrons and holes that constitute the flow of current. In insulator, we have almost zero flow of electron, so almost negligible flow of electron, but due to some minor free electrons, that's a little bit flow of currents in the insulators. That can be flow of currents depending on the circumstances. Now, for temperature coefficient of resistance, conductors are said to have positive temperature coefficient of resistance because when temperature increases, their resistance increases. But for semiconductors, when temperature increases, their resistance decreases. So they are said to have negative temperature coefficient of resistance. And for insulator too, we have negative temperature coefficient of resistance. All right. And for charge carriers in conductor in the conduction band, in conductors, we have completely filled charge carriers, okay? And for semiconductors, we have partially filled, and then for insulators, we have completely vacant charge carriers in insulators, okay? Charge carriers in valence band. In conduction band, we have completely filled in conductors, partially filled in semiconductors, and completely filled in insulators. For valence band, conductors, we have almost vacant charge carriers. Semiconductors, we have partially filled, and insulators, we have completely filled in terms of the charge carriers in the valence band. So valence band of conductors is almost removed, and all of them have almost gone into the conduction band. Now we have examples of these various materials. We have for conductors, we have copper, aluminum, graphite, etc. And for semiconductors, we have group 4 elements such as silicon, germanium, arsenic, etc. And for insulators, we have paper, rubber, glass, plastic, and so on. And for applications, conductors are applied as conducting wires for transformers, electrical cores, etc. Semiconductors are applied as diodes, transistors, and optocouplers, etc. For insulators, we have sports equipment, home appliances, cable insulation, and so on and so forth. So that is what we have. For the Fermi energy level, there are specific energy levels associated with each shell and orbiting electron with the atomic structure of each and every isolated atom. So this energy level associated with the shell is different for every element. So the maximum energy that the electron possesses at a temperature of 0 Kelvin is referred to as the Fermi energy level. And this energy level for any particular material depends on the number of available states and the number of electrons that must be accommodated in them. This is represented as EF, energy F, that is Fermi energy level. For a metal, Fermi energy level is the uppermost occupied energy states at absolute 0 of temperature. For semiconductor, the Fermi level is situated in about middle of the energy gap, And for insulators, Fermi energy level is situated in the band gap, and that explains why they do not conduct electricity. So that is how we can classify materials based on their energy structure, the energy band structure. So don't forget to like and share this video. If you haven't subscribed to the channel, don't hesitate to do so and click the notification bell. Until another time, I say thanks for watching. Bye-bye.